All right. Hello, everybody. Hey, Manchu. Good to see you again. Welcome to one of the new TAC training classes, Parallel I/O, with Ritu Arora and Robert McClay, with supporting help from John Kaz and several other folks here at TAC. We're trying something new in terms of our webcasting, so we're actually broadcasting this through a Google Hangout. The video will be available right away on the YouTube channel right afterwards. So I'm not going to take up too much of your time. I'll go ahead and let you get right to it.
One quick technical question. Now, how do I get to the presenters now?
You can only like this. That's all I got.
Oh, okay.
Mm-hmm.
So we don't have presenters mode for you. Even on Mac.
And there you go. It's about a 30-second delay.
I navigated to this? Okay. Hello, everyone. My name is Ritu Arora, and my colleague Robert McClay, who's going to be doing the next part of the tutorial after I'm done, is sitting behind right there. And together we will introduce you to the very basics of parallel I/O. If you came expecting intermediate or advanced knowledge, then I'm sorry, we'll disappoint you. We'll touch over very basics of Lustre file system, very basics of MPI I/O, HDF5 and T3P I/O, and we will talk about. Sorry. And we will talk about I/O strategies and best practices.
Okay, just hold it.
And we'll have 2 lab sessions. So before I even get started with what I have to say, let me ask you, are you aware of any scientific application that does not do that does not involve any input or output? Anyone? And the winner is Frank. Frank is going to tell us something. Is there no right?
What would be the point?
Yeah, what would be the point exactly? So practically every scientific application involves I/O, either for reading initial conditions, writing numerical data. And when you look at the equation that's there on the second bullet, it says that the total execution time of your application is a sum total of computation time, communication time, and the I/O time. However, doing efficient I/O without stressing out the HPC system is challenging and often an afterthought. Now, every week, about 3 to 5 users are suspended on Stampede, either for crashing down something. I mean, mostly file system-related issues is what gets them off Stampede temporarily. So that was the primary, or one of the motivations behind introducing parallel I/O in a basic manner first, before we go on to our advanced stuff in following training sessions. So let me give you a brief overview of the modern HPC cluster. So you would see that you have a bunch of processors, like hundreds of thousands of processors, and then those are connected via a fat arrow, I'm saying arrow at the moment, through the network, and then a lot thinner arrows to the few hundred spinning disks. Now think of this as the connection between the processors and the network is like a superhighway. And the one between the network and the spinning disks is like your country road, which is a lot smaller. Now, if you need performance, what would you do? You would be, just increasing the number of spinning disks on one side or just adding more memory is not going to give you more performance. So you need a solution that is scalable, gives you high throughput, and that's where something like Lustre comes into picture, okay? Because we need a magic to make the collection of spinning disks act like a single disk for the user. So this Lustre file system, let me quickly show you how its components are arranged at a high level through this diagram. So you see that, let's focus on I wish I had a pointer. John, do we have a laser pointer?
Yeah.
Just remember that your remote folks can't see your laser pointer.
Oh, then maybe I'll use the mouse. I'll use the mouse there. Thank you. I'll use the mouse there. Thank you. Thank you so much. So if you look at the stuff on the right-hand side of the figure that we have there, we have Lustre servers, we have Lustre targets, okay? Now Lustre servers are of two types, MDS, which is metadata server, and the object storage server, which is OSS, okay? Now each of these, like in case of object storage server or OSS, is talking to an object storage target, which are bunch of spinning disks, okay? So each OSS serves up to 2 to 8 OSTs typically. And each MDS, or the metadata server, is talking to just one MDT or metadata target. Now in Unix world, if you're aware of the file systems, you would know like there's something like inode, right? So you can think of, you can draw a parallel comparison here. All your inode information or your name of files, directories, paths, permissions, all that is considered as metadata. And that goes into this guy called, that's stored here like in metadata target. And MDS acts like a conduit between the network and the MDT. Okay, so far so good. Now let's move towards the left-hand side of the diagram. There's a network. So these MDS and OSS are connected to the rest of the compute nodes through a network, which could be Ethernet or InfiniBand, let's say. On Stampede, we have all InfiniBand. And then, if you go further towards the left-hand side, you would see that there are compute nodes. There's the RAM of the compute nodes. Okay, that's the memory. And then if you go further towards the left, those are the Lustre clients. Okay, those are the application processes running on the compute nodes. So basically, we divided the complete Lustre architecture into broadly, like mainly 3 or 4 components. So you see, when you are working on Stampede on the login node, when you log in, you can think at that place as where you're running your Lustre client, okay? And then there, each processor, there are 4 levels of memory you can think of. Each process has its own register and cache. Then they have a memory or RAM, and then they have secondary storage. Let's say, for example, Corral, okay, for example. And then you have tertiary storage, let's say like Ranch, which is offline storage. So this diagram just gives you an idea that if you are if you are having an application process and you're trying to store something, the arrows show you the direction in which you're moving, and you would see that you have to go across network to the MDS. Okay. But the rest of the arrows down there could be misleading. They might tell you that, okay, maybe everybody is trying to make a connection with OSS directly. No. Okay, this is how the connection is made first. So when there is a Lustre client trying to talk to an OST, or maybe when you're trying to get your file from the storage device or trying to write a file there, you will first send a request. Your request will first go to MDS, metadata server. Metadata server will then help in opening or closing the file or whatever other tasks are required, the housekeeping activities. Once it has opened the file for you, then it passes on the handle to the other stuff, as in the OSS. Now OSS then talks to the application processes directly, and you bypass the MDS for future writings. However, when you're opening, let's say, lots of files or closing lots of files repeatedly in a loop, it's this guy, MDS, that gets stressed out, because there's just one MDS that's servicing all the users, right, and all the requests. So if you if you open files too often and close them too often, and create too many small files, this MDS is the guy that you're making unhappy. So we run Lustre file system on TAC resources. There are other file systems like GPFS, NFS. I'm just going to tell you about Lustre basics here. So each Lustre file system, as I told you, has they have like components as OSS and OST, where OST is object storage target, And again, those are a bunch of spinning disks. You can think of those as RAID 0 arrangement that they have there. So if you look at our different file systems, home, work, and Scratch, Scratch on Stampede has 348 OSTs. Work has 672. Thankfully, with our latest stockyard file system, you get that much. And home has only 24. On Lone Star, on the other hand, we run NFS on home. And for work and Scratch, we have 30 and 90 OSTs for Lustre. Okay? So it's very easy to tax the file system without really doing a lot of computation. We could be doing an innocuous ls, right, in a very crowded directory. Now that guy, you might not realize, is hitting the MDS. It is trying to stat the MDS every time you do an ls minus ltr or something like that. So in a very crowded directory, we recommend that you rather use something like bin ls, like this guy, okay? And also, like if you are, as I said, if you're trying to open and close too many small files in very few milliseconds, you're again stressing the MDS, because it's just one guy that's servicing all the requests, okay? So too often, too many is bad. And if you are writing a file, it's preferred that you write one large file, and you store it like, of course, I'll talk about striping later, but suffice to say now that when you're trying to write something, try to write it out in large chunks. And try to write it out from Scratch, because Scratch has more OSTs. So that was about the basics that I had to mention. Yeah.
Do you want us to ask questions as you go along?
Sure.
Can you go back?
Yeah.
So what's the difference between ls and bin ls? I realize that ls is alias, but it looks like it's just alias to bin/ls with some option.
Robert?
Yes, you're right. The option is
The option, that color thing?
yeah, that's tagging every file.
So if you see, do you see blue colored direct, like files, some executables in green color, some
No, I
in,
get rid of that.
yeah.
I understand.
Yeah. Okay. Yeah.
You just mentioned that there are more OSTs on Scratch. Is that right?
Yeah.
Because I
Yes. Like let's go to this diagram here. So if you look at Stampede, there are more OSTs, like 348. But the slides that now work has most OSTs. So typically, like you would do write and read from Scratch. But recently, we updated work to the stockyard system, and it went to 672. So now I think it's good if you work from work. But again, there might be file quotas. On Scratch, it's like unlimited. So yeah, that's why I recommended Scratch. So the goal of parallel I/O is to use parallelism to avoid I/O bottlenecks. And parallel I/O by itself can be hard to coordinate and optimize if you're working at the very basic level of POSIX I/O interface. Okay, even working at Lustre API interface to me wasn't that high level. Some people like just working at that level. So people like me who are a little lazy, or maybe other people also who are not so lazy, but they just want to get done with their work more efficiently, they would want some middleware in between the low-level Lustre API, POSIX I/O, and which is sitting on top of the hardware level. So therefore, there are software stacks out there like MPI I/O, HDF5, NetCDF, to name a few, and Tax's own tool called T3PIO that Robert will mention about. So instead of working directly with the low-level stuff, you get a higher level of abstraction by working through these high-level API. MPI I/O basically lies at the base of HDF5 and T3PIOs that Robert will talk about. Let's look at some typical patterns in parallel that you might see while you're doing I/O. So, have you written a basic MPI program, Hello World program, and asked the processes to print their ranks and seen the result? How does the result look like if you are telling every process to write it out? All jumbled up. You might see rank 5, rank 6, one sentence not completing and being trespassed by other sentences from other processes. So you get gobbled up output. So what you do at times is, you might think, oh, let me just make one process or the root process do the writing part. So I might say, oh, if rank equal to 0, then that rank should collect the stuff to be written from all other processes and do the writing, right? That's the pattern I'm trying to show here. This inherently becomes a sequential process because I'm limiting the performance and scalability of my application by involving just one process in doing the writing part. So what I do is a second method. So I engage, as in I would like to engage multiple processes in the process of reading and writing data. When I say processes, I meant MPI processes. So I want to engage multiple MPI processes, let's say, in doing I/O. And the strategy is like you have one file, and each process knows exactly where to begin and where to end the writing part. And that's called the offset, and we'll talk about all those details later. But this diagram is just meant to give you an overview of how to engage. I mean, just to give you a view that you can engage multiple processes to in the process of writing just one output file. Now, how many processes are enough? Like, if you were to wonder that, then let's assume a scenario in which you have about 1024 nodes. And if you're talking about Stampede, each node has 16 cores. So if you launch your MPI job saying, I want 1024 nodes and I want to use all 16 cores on that, so essentially you're asking for 16384 I/O clients, right? And that is terribly oversubscribed. And that's what would thrash the system. Okay. Let's be a little more gentle than that. Let's say, like, instead of having all 16 cores or all 16 tasks engaged in the process of writing, let me think about, oh, how about having just one process on each node do the write part? Okay, that sounds better. This number was 16384. At least now it came down to 4 digits. 1024 I/O clients. Much better, but can we do better than that? Of course. Imagine, like, instead of engaging 1024 nodes, you're down to 160 nodes, right? And you are using just one process or task per node to do the writing part. So now you have 160 I/O clients. And in certain scenarios, you might get best I/O bandwidth with just doing this, like reducing the number of tasks that are doing the I/O. So there are techniques like data sieving, etc., that I might mention while I'm talking about collective I/O, but I'm not sure how much time we will have. But this is just to tell you that there's a balance that you need to strike when you're trying to do parallel I/O. So here, like with this one, like 160 nodes and having one task per node, the problem is it might look good theoretically, but the servers are shared. And you still have to move the data to the other tasks, right? Even with this one. Okay. Now, talking about Lustre. Lustre, the parallel file system I told you about, that guy not only manages the hardware resources, it gives you a logical view, a logical unified view of your storage resources, such that you don't have to think, as a user, you don't have to think in terms of OSTs. Is a part of my file stored on a OST1, OST0, or where? So Lustre unifies or makes everything seamless for you. Now, but as I told you, Lustre, like what it does is, it has several I/O servers in a RAID 0 kind of configuration. So you can have a big file that you can chunk down, and you can have, that's called striping, and you can set the size for the stripes. If you look at this diagram on the slide, so we're assuming that this file is 8 MB, and we want to set the stripe count to 4. We want to, you see the colors, there are 4 colors involved here, basically. And I'm saying that I want 1 MB stripe size. So when this file is being written on the OSTs, the color coding will tell you that everything that's color coded in blue ends up on one OST, everything that's colored on in red ends up in another OST. So basically, this shows you that you as an end user, you just set the stripe count. Now OSTs, where the OSTs are, they're mapping, the mapping of the files and the OSTs, that's handled by the Lustre. And basically you can adjust the stripe count, and you can also adjust the size of the stripe that you want to set here. So coming back to this balancing parallel I/O part, so one thing that you have to know, or just want to be aware of at this point, is that you might want to match the I/O bandwidth with the switch bandwidth. You remember that I showed you a diagram early on. One side of the network was fatter, a lot wider than the other side of the network. So basically, you have to, what we are trying to say here is, and note that numbers are not representative of Stampede. So I'm not trying to say that I/O bandwidth on Stampede is 1 Gbps at all times, and between the I/O server and the disk is 150 Mbps at all times. All I'm trying to say here is, if you have a lot of data being produced by your computational job, and you know that the bandwidth between the server and the disk is small, so what you do is you engage you stripe such that you have multiple paths between your server and the disk, right? So this can be done. So if you look at the diagram below, there are 4 paths between the I/O server 1 and the disk, right? So you're engaging like 150 MB per second paths, and there are 4 paths. So this is a lot better than engaging just one path in the figure above, which is 150 Mbps. And in order to do this, there are commands that Lustre provides. One is LFS set stripe, and I'll give you an example of how to use that on the upcoming slide. So at this point, all I'll mention is there are some default values for these stripe counts and the stripe size that are set for each system. On Stampede, for example, for Scratch, we have 2 stripes, each of width of size 1 MB. And on Work, we have one stripe by default set at 1 MB. On Lone Star, it's the same. On Scratch, 2 stripes per MB, and on Work, 1 stripe per MB. So that's the default one. But as a user, depending upon the application you're running and depending upon your needs, you can adjust that such that you can tell the Lustre how much stripes to use. So if you run this command, LFS get stripe, and pass a file name, an executable name there, like /test file, that will give you the stripe count that's being used for that file, and then it also gives you the stripe size and gives you the offset and all that information. Now look what I'm doing with set stripe command. I'm saying LFS set stripe count minus C, that's 4, and the size is 4M, minus S 4M. And I give the name of the input file. And when I run this command again, like LFS get stripe on this test file 2, I see that my stripe count is 4 now, and my stripe size is set up accordingly. Okay. Now let's quickly move. It's 1:30. Let's move to MPI for parallel I/O. So in MPI programs, like we had already discussed, you could be engaging just one MPI process to write out your file, or maybe read your file, or you could be engaging multiple processes. Now, if you remember one of the slides early on balancing I/O, I think I was mentioning that, like here, with this diagram. I was mentioning that it's good to reduce 1024 clients down to 160 clients for the I/O, but can you do any better, right? So of course you can do that, and there's a way which is called data sieving, in which you can, what you do is, that is like in the non-collective mode when you're using MPI. You have a bunch of processes that are just meant for aggregating the output from other processes. So they act as aggregators, and you can have multiple levels of aggregation in your code. It's totally up to the application designer or the software developer about the number of aggregators that they want to use for their application and the level of aggregation that they want to put in there. So imagine like this. you have 1,000 processes engaged in your computation, and you cannot have all of them write to the output file. Okay. Now, if we just reduce them such that we employ 10 processes to collect data from the rest of the 900 processes, those 10 processes are the aggregators. I'm sorry, those from 990 processes, those 10 processes are the aggregators. But here in this example, by reducing the number of processes to too low, as in just 10, you're basically creating a bottleneck again. So it's basically totally up to you how you optimize or level that up. You don't want the number of aggregators to be too less, and you don't want them to be too high. And that sweet spot is something that will depend upon your application, and by hit and trial is what you need to figure out. But I can give you some stats in the upcoming slides on that. And you can imagine that when you're doing reading and writing in parallel, it's just like sending and receiving messages, right? So basically, this MPI machinery is good for parallel I/O because it already lets you do sends and receives. It lets you do broadcast. It has collective modes which are highly optimized and point-to-point mode. So I will go more into those API and collective and non-collective mode in the next upcoming slides. But just to give you a background, MPI I/O wasn't like a fixture in MPI from the beginning. It was introduced to MPI by the MPI II standard in 1997. And it interoperates with the file system to enhance I/O performance for distributed memory applications. So let's take a look at this diagram that we have there. Let's say we have a file, and we have n processes, MPI processes, that we want to engage to write to this file. And the count begins from 0 and stops till n-1. So there are 3 ways of positioning where the read or write takes place for each process. One, we can use individual file pointers. We can use like MPI file seek and MPI file read together. Or we can use we can calculate offsets and use the API MPI file read at. Or I can have access to shared file pointer, which I'm not going to discuss in today's session. We have, just by the way, just a shameless plug, we are having an Exceed tutorial at Exceed 14 conference on the same topic. If you attend that, we'll have more information. And it's an intermediate and advanced level tutorial we'll be having there. So, so let's look. So that was just to tell you like 3 modes, and we will be using 2 out of these 3 modes in this exercises that we'll see soon. So first of all, how many of you are C programmers and how many are Fortran? Fortran. Then if you have a copy of the slides, you might want to go to the end of the slides. There's a section which is like for programs corresponding to the C programs that I'll show in the upcoming slides. So you might want to flip to those. So and API-wise, just as a general information, majority of the subroutines, the MPI subroutines in Fortran, they differ with the C routines in one argument, that is IERR, the last argument that you put in there. Okay, and except MPI WTIC and MPI WTime, I think probably that's the only difference between the C API and the Fortran API. You just have one more argument. And that's why I haven't repeated it here. So I didn't mean to leave Fortran guys out, but just for brevity, I'm showing the C API part. So like you do like programming in C, first, like you're doing file I/O, first you will open a file as a first step. And when you're opening a file, you have to specify, okay, which mode do I open the file in? And then you need to have a file name. And then you do your operation, whatever you're doing, reading or writing. Then you close the file, basically. This one in MPI is not much different. So you have to first open the file, get a file handle, okay? And then you have to, at that time, tell what is the mode you're wanting to opening the file in. There are a bunch of modes, and I've put just 4 here. Read only, write only, read-write mode, and create mode. So for me, like when I'm creating a file, for me the rule of thumb is I always OR like if I want to open a file for writing, I'll say MPI mode write only pipe MPI mode create. That is, if my file doesn't exist, write it. So that is what you have to use, and you can combine multiple flags like that, like pipe in C and plus in Fortran. And the API for closing the file is MPI file close, and it takes one argument, which is the file handle that you create using MPI file open. So after opening the file for reading, then as I told you, there are 3 ways to get to the place where you want to start writing. So, and we are looking at 2 modes. So we are looking at the combination of MPI file seek and MPI file read, and MPI file redact. So if you look at the syntax, if I have MPI file seek, it takes the file pointer as the input, and you have to specify the offset for each process, like where do each process starts writing. And then there's an argument called whence. Whence is basically for updating the file pointer according to 3 types. Like, is it like MPI seek set, seek current, or seek end? Basically, it updates the pointer, whether the pointer is set to offset, or whether it is set to current position plus offset, or whether it is set to the end position of the file plus offset. Okay, and you can use, you have to use, if you're using seek, if you're using MPI file read, you have to have MPI file seek with it. Now, MPI file redact combines both of them together in one API, and in here you will have MPI file h, the handle. You need to specify the offset. Then you give the buffer, just like in MPI file read, and you specify the count, as in how many, what is the count of the data I'm trying to read, and the data type. Any primitive or derived data type can be provided here. Then you can have MPI status. You have to have MPI status as the last argument. And do not worry if you're not understanding any of this. Probably this will become clearer with this beautiful example. So all these examples are there, will be provided to you during exercise or the lab session, and you'll be able to take a peek at the files, compile it, and run it. But bear with me for a moment through this boring explanation of the code. So as I said, the first thing that we have to do is have a file pointer. So that's why I have MPI underscore file fh for declaring the file pointer in my MPI program. Then I have rest of the stuff. I mean, of course, I cannot have any MPI API without calling MPI init, right? So I ought to have MPI init in my program. Then I have MPI comment size. I had comment size because I want to calculate how much of the data does each process gets to read and write. I want to calculate offsets on the basis of the rank. So in order to do that, my formula is very simple. I'm assuming everything is very nicely divisible, which might not be the reality, but let's assume that for the time being. So let's assume I have buffer size. I'm going to have a file size set to 80. So I defined hash file size, defined file size 80. So when I do like file size divided by size, what is size? What is size here? Perfect, awesome class, yes. So size is the number of processes participating in my MPI communication, okay? So I grab that number and I divide 80 with that number. So if I have 4 MPI processes or tasks, I divide 80 with that. So 80 divided by 4 is 20, right? So my buffer size is 20 here. Then what do? I need to compute how many integers. I know I'm working with integers because I'm writing the program. So I want to find the number of integers I'm dealing with. So what I do is I just divide my buffer size, or the chunk that I just got, 20, with the size of int, which is 4, right? So I get 20 divided by 4, 5. So basically I'm trying to arrive at the number or the amount of data that each of my process should be writing. So I allocate a buffer, int buff, with those many integers. Are there any ancient C programmers, as in with ancient, those prior to C99? So you might think that, oh, what is she doing? She has int buffer, I mean a declaration of a buffer down there after the integer declaration section and everything. This is allowed in C99. You can have an allocation of the buffer like this. Like you can, you can defer the declaration of a buffer down in your program, and you can also have dynamically allocated buffers like arrays in your program with C99. Okay. So coming back to my MPI program here. So I have MPI file open statement. Now this guy takes some arguments. MPI com world, what's that? The default communicator, right? For the MPI programs. So I've passed my default communicator as the first argument, the name of the file I want to work with as the second argument, the file in this example. Then I pass the mode in which I want to open the file in. That's MPI underscore mode underscore read only. Then I have MPI info there. I'm using MPI info null. You can set it to different things, and we will talk about that in maybe 7 to 8 slides later. So we have MPI info null there, and we pass the file pointer. Okay, that's the handle to the file we opened with &fh. Now that my file is open, what do? I told you that I could be using seek with read, or I could be using read at. Now in this program, I'm using seek. I'm telling my pointer to progress at a particular point depending upon my rank, right? So I want to make the writing process my rank dependent, dependent on the rank. So I say file seek will take fh and its rank multiplied by buffer size. So let's do some maths, quick mental maths. So let's take a very simple case. I have 2 processes and I have 100 as my file size. So where should my process 0 start writing from according to this formula? Rank multiplied by buffer size. Perfect. And my process 1? 50. Perfect. Exactly. So that's what I'm trying to do. I'm trying to set where the processes want to write by multiplying the buffer size with rank. And then I have MPI seek set, okay, which is the most basic mode. I'm trying to tell, this is the whence argument I explained earlier. Like what exactly do I want to do with my pointer? I want to write it just where the offset is set to. Okay. Then I have MPI file read API that takes file handle, the buffer that we created here, like where my mouse pointer is. It takes that buffer in. It takes the number of integers or the count, okay, and it takes the data type, which is MPI underscore int, and the status argument. This is MPI status that we define up there, and it's a required argument, okay, and we pass like the address of that variable there. Are you guys familiar with request objects and status objects for MPI? Good, awesome. So that's what is going on in here, and all I'm doing is I'm printing the rank, and I'm printing a value corresponding to the rank in the buffer. Let's say if my rank is 0, I want to print buffer 0, the element 0 in the buffer. If my rank is 1, I want to print buff 1. Basically, it's a silly thing I'm doing, but that's all it does. This printf statement, and then I'm closing the file. Then I call MPI finalize. Voila, we have the first MPI program to open a file in read-only mode. Okay, so just to summarize, yeah, you have a question?
Would it be potentially possible to do work between the seek and
Yeah, you can do that.
It's just getting it ready to
Yes. So here, just to summarize, there's a step to open the file. There's a step to seek to the position you want to write or read at, and here we are reading. So we will say we want to have an API that gives me the position of where to start reading. Then I will call the API, that MPI file read, and once I'm done, I'll close the file. Just simple as that. And if I were to do the same thing, instead of using MPI file seek and file read, I could as well just use MPI file read at. Rest of the stuff and the explanation is exactly the same, except that now I'm using file read at instead of using 2 API, file seek and file read. Okay, and This combines file seek and read in one step for threads, and that's pretty much all you want to know at the moment. I don't want to go into thread safety, etc. But that was for reading. Now for writing, first of all, again, what do you need first and foremost? You have to have a file handle, right? Then you have to have the file opened in an appropriate mode, okay, which is the read mode, and if needed, the create mode. And for writing purposes, you can use MPI file set view, just like we had to seek to a location while reading. Here, for writing, we have MPI file set view, and then MPI file write, these two APIs. Or I could use MPI file write at. The choice is yours. So if I'm using, let's look at the syntax of set view. I know this could be very boring, but just bear with me till we go to the next interesting example. So here, file set view takes few arguments. It takes file handle, the offset, and the data type, and the file type. And that is interesting, and we'll talk about that soon. And then it takes the data representation, and then it takes the MPI info object as its argument. Okay? And I'll explain those to you as we progress through future slides. Then MPI file write, it just takes file handle as input. It needs to have the buffer, address of the buffer in which you want to do the writing part, and it needs to know what's the count of the data that you want to write, the data type, and the status object. Then you have MPI file write at. So MPI file write at is basically a combination of set view and write, if you will. So it takes the file handle, offset, the buffer, the count, data type, and status as its arguments. Okay, coming to this example. Let's see what's going on in here. So, is there a volunteer who can tell me on which line number am I opening a file or creating a file handle? Let's go one by one. On which line am I creating a file handle? Hint. Line 5. Okay? That's where I create the file handle. Then, what am I doing here? I'm just initializing my MPI environment again. Then I'm allocating space for my buffer. And this is not the full code. This is just the snippet, I think, here that I put in. And the full code will be there in the file called writefile1.c that you will see when we get to the exercises. And all I'm doing here is, in the buffer, I'm setting that to the value of I in the loop. So it goes from 0 to n, so the buffer will have values 0 to n, basically. And then I calculate the offset, just like we computed that for the read part. And I have this file open statement, all in bolds. Okay. What does this guy take as the last argument? What is this? FHW? Perfect. Thank you. You all rock. So that's the handle that we created above in line number 5 that we pass here. And you see, in place of MPI info object, we have MPI info null. At this point, we're not interested to pass any hints or any extra information to the MPI environment. All we want is MPI info null here. And look at the mode in which I'm opening this file in. I say MPI mode create pipe MPI mode write only. Okay. So first, like if the file doesn't exist, I'll not run into error. I'll have that file created, and then the write will occur from that point on. And I'm passing the default communicator MPI com world as the argument, and data file is the name of the file I want to write to. And again, some silly print statement in there. All I'm trying to print is, did I calculate my offsets corresponding to the rank? I'm such a paranoid. I just want to check that every time. And this is one place where people make errors. They might be thinking, oh, I computed offset right, and why is my program giving segmentation fault? It's very often due to this guy, the offset. It's miscomputed. Either you're asking to write to the region that does not exist, or something like that happens. So what I do is I always check my offset, like, is that what I wanted for a particular rank? Okay. Then I have file write at statement, wherein I pass the file handle, I pass the offset, that I computed at line number 15 of the code. Then I pass the buffer that I created up in the code, and I pass the count and divided by size there. I pass the data type and the status, and then what do? Close the file. So basically, I'm writing buffer. Okay. So contents in what are the contents in the buffer? To refresh your memory, let me go up. Let's see what we wrote in the buffer. We wrote 0 to n in the buffer, right? And this buffer is what I'm trying to write to the file. Okay. And that's what I do, and I close the file. And when I run this program, see what I get. So I compile it using MPI. When I run it with 4 processes, I get rank 0, offset 0, rank 1, offset 16, and all this stuff tells me, okay, my offsets are computed right. And now it will, and at end of the job, you will see a file created with the name that you passed here, and it's data file when you run this program. Now, how will you see the file? What's in the file? It's going to be a binary file. Okay? So either you can use hex dump or you can use octal dump. The command that I put on the screen is hex dump. So you see, because for each rank we set buffer to 0 values in the buffer to 0 to n, that is 0, 1, 2, 3. This, because there are 4 processes, my count will start from 0 and go till 3. So that's the content of the buffer, and it's written as expected. See, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so forth. Right? Now, let's talk about file views. Or should we take a break here? Do we have a question here at this point? Yeah.
I had a question. When you were reading your file, you told it that the file size was 80. So that meant that it had 80
bytes.
Integers?
Bytes.
So usually, I mean, for big files, obviously, it's not some simple number. So I assume.
Of course. Yes. And that's a very good question. Thank you for asking that. In that teeny-weeny example, I knew I'm going to have a file of 80 bytes. But in practical situations, you might want to call an API called MPI get file size.
Okay, that's right.
Yes. So get file size will return the size of the file that you're dealing with. Thank you for the question. So just for the remote audience, there was an interesting question that in-person participants asked here. The question was, how do we get the file size if we do not know about it upfront? So the answer is you can use an API called MPI file get size, or get file size, sorry, and that will return the size of the file. Okay, let me take a quick break and take a water sip. So if there are any questions, yeah.
So once you use MPI file safety, I guess if you want to change that, you will use it again before the write, or if it remains the same, you can one small MPI file safety, and then you just keep writing using MPI file.
So it depends totally upon your application. If your application is such that you want to open the file once, set it once, set the view once, and you want each process to write it just that way, you just set it once. However, if you want to keep on opening and closing the files at different points, you want to be resetting the views at different points, it's totally up to you. There's no restriction to that. Okay.
Great.
Yeah.
So at the MPI level, you're exposing where in the file you want to write. But the stuff at the Lustre level is not exposed. You're not considering stripes or anything.
We can, and that's exactly what MPI info object helps you to do. So I'll talk about that in one of the slides. So there's an API using which, from within MPI code, you can set Lustre API stripe count and width and then size. So it takes like as an argument what you want to do. As in, I want to set the stripe count. Let's say pass that. You pass how much you want to set it to. So there's an API to do that, but the caveat there is your MPI should be built with Lustre code. On our systems, we do not have that problem because I think it should be built like that.
Are these all exposed in MPI values or
Which one? MPI.h.
these are okay.
Yes.
And the next level would be, is it a different?
No, just MPI.h. That's what you call. Is there any other question? Okay. Just to make sure that you are with me till now, let's do a quick recap of what we covered till now. Okay. So I told you that you have to, first of all, in order to do anything with the file, the first thing is to create a file handle, right? Second thing is you have to open the file, right? And what are the modes? Can anybody name 2 or 3 modes in which you can open the file in? If you're reading. Thank you. Had I had like a prize, I would have given it to you. Thank you. I'll just give you a smile. Thank you. So here, now coming back to the file view part. So we had another question from the audience here. So the question was, can we keep on setting and resetting the file view multiple times in a program? Can we? Of course, you can do that. You can open the file and close it depending upon your application needs, and reopen it at a later point in your program. Okay, and you could be setting the views differently at different positions. So I'm not sure if I'll have time, but if I have time towards the end, I will show you how to do distribution of 2D array, in which you can create a virtual topology, and then okay, we'll go there if we have time. I'll better not talk about it and break the suspense. So when we have processes that need to write to a shared file, we assign regions of the file to separate processes using MPI file set view, and we have already used that in the with the writer that we had. And there were a few arguments in there that I told you I will come to soon. So file views are specified using a triplet: displacement, E-type, and file type. Okay. Now displacement is the number of bytes that you want to skip from start of the file. Okay. This is just like file seek, if you will, in C. I do not know the analogous of that in Fortan, but in C, you will have to, if you have to skip to certain bytes, you can do such I mean, this displacement thing is similar to that. And E-type is the unit of data access. It can be any basic or derived type. It could be int or your structure that you create using MPI derived types, okay? And then your file type. It specifies which portion of the file is visible to the process. Okay. Now look at the API again. It has MPI file FH, MPI file offset, which is the displacement. Okay. MPI data type, which is the E type. And as I said, it can be either the primitive type or the derived type. Then it takes the file type as an argument, and we will come to that. Well, no, I can mention about it right here. Okay. So there are basically 3 types for the file type that you can specify: native, internal, and external 32. In very short, if I have to summarize this native, internal, and external 32 business, all I will say is external 32 gives you the portability across different MPI implementations. It's a different file format, so there are overheads. So what happens is if you have some data in your memory and it needs to be written, with external 32, it will be first converted to the external 32 representations before it's written. Okay, so that's what external 32 does. It has overheads, but it gives portability across different MPI implementations. Then there is an internal mode, and there is native mode. Native mode just writes as is, like however my data is in the memory with the same precision, I just write it out. Internal gives you slightly more portability than the native. So if you have to run across different architectures, I can either use internal or external 32. If I'm sure that my MPI code is just for this particular architecture I'm running on forever, I'll just hardcode native. But as I told you, I'm such a paranoid. I'll either always pick internal or external 32, even though there are some slight overheads involved, because I just want my code to be portable across different MPI implementations. All MPI implementations, if they for external 32, I think they conform to that format. So you will not see any differences. Yes.
So does that mean that I can only read once a file is written under MPI? I can only read using an MPI implementation, or can I just use a serial implementation to read that?
So basically, depends. If it's a very tiny file, like we use octal dump or hex dump to get the binary thing out of that, we could do that. Just run a command and convert it. Okay. And other way is to have another MPI program to open it and read it.
So it can't be read with like a serial C.
So as long as, so it could be a serial program, you're running on just one process, but you could have MPI API. Because if you think about running your MPI program on just one process, it's a special case of a serial program, right?
It has to be
It has to be done that way.
Yeah, at least that's all I have tried. I have not attempted to use any other program. I'm not aware of any other utility besides hex dump, octal dump, or just using MPI to revert the data, or maybe to open that.
I have another question about this slide. So when you define file type, in the middle it says file type specifies which portion of the file is visible to the process, but then down at the bottom it seems like file type is sort of defining the format. Those two don't seem to match, those two definitions. File type.
Oh, okay. I'm sorry. I goofed up here. So file type which you read there is correct. I'll come to that. But data representation is another argument here. Let me go back to file set view. Here. You see this argument here somewhere, char star data rep. That's the guy for native external 32 and other things. So for remote audience, I made a mistake while I was talking. I wasn't mindful that I was mixing names. So I was actually talking about data representations when I mentioned native external 32 and the internal formats of writing the data. So that's about it. And file type is basically, again, the data type, the derived type, or your primitive data type that you have, int, float, long, that thing.
But how does that, it still doesn't make any sense if it's int. How does it specify which portion of the file is visible to the process? What does that mean?
Okay, let's take an example. Let me see if there's a marker and if I can do some board work. No, probably not. Okay, let's take a very simple example. Again, of 100 items to write, okay? And let's say all of them, let me take a better number. Let's take 400 items to write, okay? So if I have two processes, and all of them are integers, so if I have two processes, what's the data that each gets to write?
How many did you have? 1.5 and 1.5.
So yeah, I started with 400 bytes to write, and I have two processes. So how do I know how much data each process is writing? 400 divided by 2. I get 200. Now you remember I did another division. I divided the data with the type, size of int. If you were writing a size of double, it would be divided by that. So now you can map those two together. So if I'm writing one integer, I'm basically consuming 4 bytes. So when I specify my offset here, that's a number, a 50 or something like that. And that has to be multiplied by the number of bytes to get to the exact location. Okay. So, yes?
Why use MPI file set view instead of using seek or write? What are the advantages?
Okay. So here I was showing you two ways. So if you have to use file write, then you use file set view. However, if you want to use write at, with that API, you do not have to use set view. Does that answer the question? They're just two different ways.
There's no advantage.
Yeah, they're just two different ways. In one, like you just write two API, and in one you write just one API, combine everything in one place. It is just for information, so that because most often you're not just writing MPI programs, you're also reading it. so that you know what the other person did. If they had both set view and write, you should be aware. So if I were writing the program for myself, I would just use write at or read at and reduce the work of writing two different APIs. Or I would do something better. I would just use collectives.
And there's no overlap between whether you use the two.
No, I don't think so.
Isn't using MPI files if you're giving flexibility to define maybe writing intermingled, interlinked?
It does give
which
that.
we cannot do otherwise. I guess.
Well, there are ways to get around that with the logic. Like you have to have multiple APIs and multiple topologies to do that. But that could be considered as an advantage. That's just right. But there are ways, like if you just have to live with at, you can find ways of, instead of having everything apply at the group communicator, which is MPI com world and the default one, you could have multiple smaller groups, each having a different virtual topology. And you could be having them do different things with different views. Different views or different write at things. Okay. So, so the audience here mentioned a very good point. She mentioned that one advantage to her with respect to using views was she can mix. She's not tied to one view across the program, whereas with offset and with write at, it's just one view that's fixed. But I told her that that's a very good point and a valid point, and I think that can be considered as an advantage. But if you're just using write at, even with that you can live with that too. There are ways. There's more coding that you have to do, more changes that you have to make at multiple places to make that work. Okay. So let's go to this example of writing file, and I think we did that already. I think we just covered this one, maybe not. Okay, this is another example for writing a file. So here, let's say we have, again, at line number 5, we are having a file handle. And here, I think I'm trying to show you how to use, I think it's the same example I ended up having at 2 places, set view and write. Oh. No, this was write at. I showed write at example first. And now I'm just trying to show you the same thing using set view and write. So everything in the example write file at is the same till line number 17. From line number 18, you would see that I have 2 API, one with set view and one with write, in order to do the writing to the file named data file 3. And I'm opening this file in create mode and write only mode. So basically, that's all to it. Just to demonstrate how to use 2 API in 2 different lines rather than having 1 API write it to the job. And when I run this program, you see, I again got like my offsets calculated. I checked the offset. So always check the offset if you want to make sure that your data is being written and read correctly, because then with hex dump and octal dump is what you do next to read the binary file. And I'll have this command on the slide when we do the lab exercises. Okay. So just a quick note about atomicity of read and write operation. So you can use the API MPI file set atomicity, and you can set it to either 1 or 0, so that only one process can access the file at a time. So when atomic mode is enabled, MPI I/O almost guarantees a sequential access to that particular file. And of course, what will happen? You're going from parallel to sequential, so your performance is going to drop. And note that this is a collective function, so when you call this, it should be visible to all processes. Yeah.
If you don't use this, is it by default 0?
Yes. Collective I/O. So collective I/O is a critical optimization strategy for reading from and writing to files in parallel. And unfortunately, due to time constraints, I will not be giving you examples on that. I'll just be mentioning those. So treat this session as a trailer. I'm just introducing you to what exists. and maybe now you know what to look for after the end of the session. So there are MPI APIs to do collective I/O, and these are optimized by the implementers such that you can do data sieving, as in aggregation of depending upon automatically for you, depending upon the size of the data and the size of your COM world. Okay, so this is particularly effective when the access of different processes are non-contiguous. So one thing I should have mentioned early on, but I think due to lack of time, we didn't have it on the slides, that your performance depends if you're reading contiguous or non-contiguous reads and writes. It depends, non-contiguous reads. So if you are reading from the memory or you're reading from the OST, so if your data is not non-contiguous, as in if it's contiguous, you see a lot of performance gain as compared to doing like in a non-contiguous mode. So the collective API for doing MPI I/O is MPI read all, write all, read at all, and write at all, in which all the processes participate in the reading and writing operations. And just like with any other collective API, this API should be visible to all processes. So one common mistake or common source of error that I've seen is when people put these API inside if statements, like if rank equal to 0, MPI file read all, something like that. Or maybe they do some they put something else in if statement, and these commands, these collective functions are not visible to processes with all the ranks. So that's the most common source of error that you want to avoid. Excuse me. And the signature is same for all the, as in the non-collective versions, so that's why I haven't put it there. So besides that, I was telling you earlier, I think you had a question about info. Somebody had a question about info. You, Frank?
Really quick question, but just MPI file open, does it lock on all the processes then?
As in?
When you're opening it, when you're using MPI
file open?
Yeah, does that lock on all the processes until the cluster says it's good?
No. As in, if one process is done, let's say if there are 5 processes, and you open a file, let's say, for reading on one process. So in that case, it does not affect. If you're opening it for writing, of course you have to see how it affects. For reading, there's no need to block.
Or if it's a new file.
If it's a new file. So it depends, like if you're done writing your part, you can always go back. Right? So if there are 2 processes writing simultaneously to a file, one process is done, then it doesn't need to wait for the other process. You're just writing to a file. They don't need to sync up.
Oh, and okay, that's not going to block this.
Yeah, yeah. So,
but how about if there is another input output following that command? Will it wait for the previous one to?
So that you have to handle programmatically. So you have to put a barrier. You have to make sure that if the file that you're writing to has it not been, if you're doubtful that it might not have been written completely till that point, have a barrier. Or put a lock. No, not a lock. I'm sorry, I'll take that back. Just a barrier would be fine. So MPI file open, file set info, and file set view will help you pass extra information to the MPI implementation. And these are basically meant for improving the I/O performance. And hints are optional. The MPI standard does not say that you have to have this particular MPI file open implemented in a particular fashion. So implementations can choose to ignore the implementation. It's optional, and they might have different implementations which might not conform with each other. So you can specify hints, but the implementations can ignore them. So note this point. So just like when you are working in C, as an optimization option, you can mark a variable to be a register variable to be available for faster access. But the compiler has the full freedom to ignore that request. Likewise, here also, all these hints that you give, those are up to the implementation to obey or not to obey. They can be ignored at runtime. So MPI file get info is the one, Frank, that I was going to tell you about. That's the guide that you would use to set luster information. So you can set like striping unit and striping factor with this, and this slide shows you an example for that. So setting stripe count in MPI code can be done using MPI info set, and it takes 3 arguments. And the syntax that you see on the slide might not be the right one. So here you see MPI info set all in lowercase, which is wrong, and this should be like this. In Fortran, I think it is correct, but in C it should be like this: MPI file set info. Okay, so that's what you put there, and you pass 3 arguments: MPI info object, which is MPI underscore info that you pass there, and you pass a string to tell what is it that you're wanting to pass it. Striping factor, is it striping unit, or is it like a collective buffering node? So I'm not going to go more into collective buffering mode because of time constraints, but when you're working in, maybe I'll just skip this. Collective buffering needs more explanation. I did mention about aggregators, right? But at that point, I mean, if you remember that conversation about aggregators, you can just take it a step forward, wherein instead of immediately writing the aggregated result to the file, you hold it on to a buffer. And that's called like a CB or a collective buffer. And more explanation, I think, well, it's not required at this point. Maybe I'll see if I have time, I'll revisit this slide later. So basically, you can do that. You set the number of writers as with every Fortran API except MPI WTick at W time. You need MPI error objects or the I error object at the end. And that's the only difference between Fortran and C besides this case of the API. So this can be all in lowercase, and this is this notation, this one. Okay. Okay. Now let's start with the lab session. So if you are already not logged to Stampede, maybe you might want to consider logging into Stampede at this time. And when you are on Stampede, you might want to run the tar command that's there on the slide to get to the training io.tgz folder or the directory. And then after you have untarred the directory, you might want to cd to training io. That's a directory you'll get after untarring. So try this out. You see what more I have to cover.
Looks like it goes into the direct instead of training all of it.
Yeah. So just create the training directory and go into it.
Yeah.
So it's combining the copying and untarring together.
It didn't create the directory. It just put them where you are.
Okay. Okay. Yeah. They just put it there. Okay. And it will be a directory called training IO, right?
It didn't create that.
Oh, it didn't create that?
It just grabbed the file.
Oh, okay.
So we need to create the training IO.
Oh, okay. Okay. Maybe then, in that case, we should have this here. Make directory training IO. And then you don't need this guy here. Okay. So for the remote audience, people here in person, they notice that by running the tar command, you'll get all the directories just copied to the current location, and you'll not get the directory named training IO per se. So That's why I modified the slide a bit here. So before you do the tar, if you do the make directory command and then cd to that directory, then you can untar your files there. That should be setting you right. Okay. Is everybody done with this step? Okay. Yes. Yeah.
So this is say take directory MPI training file. Say chart space minus XPCF. Training slash training IO.
See, now that would be okay, but it's your stuff and it's like. And are you?
I hope you all received your project numbers. So just in case you missed that, if you registered through TAC portal, please use training-HPC, and if you registered through Exceed portal, please use TGTRA140011. And after you untarred the directory on the previous that I mentioned on the previous slide, like training.io.tgz, you will see that there's a script in there. Inside the script, you may mention your account number. That is, if you have multiple project allocations on Stampede, you might want to add your allocation, the one that we have up there, using this command, like using this sbatch -a, and whatever this name is in your case, training HPC or TGTRA140011.
Let's see, what's the syntax for specifying the project? It's hash, $, dash A.
-a. So in the script, wherever you have a minus all those 5 x's, just replace that with the number here, training HPC. It's not there? I'm sorry. Then just copy that sbatch.
So it's hash, $, dash A,
Oh,
and then
maybe
A dash.
that's for Linux. Oh, I'm sorry, that's for Lone Star.
Oh, this is a script for Lone Star.
Yeah, I'm sorry. Let me get you guys the script for. Oh, I'm just extremely sorry. Remote audience, there's a goof up. The script that you will have, that's for Lone Star, but we are doing the training on Stampede, so you'll need a different script. And I'm trying to find, how do I go to browser here, John? The browser? Oh, here. Bring this Chrome up. Okay, thank you. So maybe I'll just put this up there. John, how can we do a find on this one?
Apple F.
F left?
Apple F.
Apple F. This is Apple. This is F. Okay, thank you. Okay, that's the script. Let me make this bigger, or is this big enough? Okay. Let me just copy it and put it on the slide so that that will be bigger than this one, I think.
We can just go to the website, right?
Yeah, and copy that, paste it. Yeah.
So if we go to the TCC website and go to user services, user guides, and
Yes. Yes, perfect.
then just search down.
Search down. Yeah. I think.
That's that.
Yeah, like this. I'm not an Apple user, so I do not know the way to copy this to the slide, else I would have put it there.
Command C.
Command C.
Command C. Well, you have to highlight the command C.
Okay, Command C.
You know, the script with string 00, directly to the content.
Oh, you did?
You put it?
Yeah, I put the draft script or one draft flow and then the string 00.
Thank you so much. So now if you go to train 00, you can copy the job script from there, and the name of the job script is
Run draft flow.
run.slurm. So basically this is the command that you should be able to type there. Say cp train 00 / run.slurm and put a dot in the end wherever you are. This will copy the script to your.
Finally,
Did everyone get the script? Okay. Yes, so if you have multiple allocation, all you do is run.slurm was the name of the file. All you do is you copy this guy like hash sbatch all in caps minus capital A space and the project name. That's how you specify the project name there. This is the option. I mean, if you scroll down on the user guide, you'll find how to add your account name.
What was the project for the training?
Let me go back to the slide here to figure out how to put this in from current slide. Okay. Okay, that's account number. So maybe I'll put a note here. Copy the script run.slurm from train 00. Are we all there? How many people are still working on the script? Could you raise your hand? 1, 2, okay.
So,
C or Apple?
but I'll try to look.
So is that training performance right? Project HPC, training HPC. What's your name? Maybe we can check if we have you with any question.
Sorry, I'm just trying to look.
No. So go to the script. Say CP, no, go back. So CP space frame 00 slash
What like that?
space start. MPI so here, type your project. Yes. Trading language.
No. Yes. But there's no different ways.
No A, there's no A minus.
They're all
So you all are on TG TRA 140011 allocation. So please do not use trailing HPC. Please like to put everybody under TG allocation.
One second. Just make it. Anything?
You have the script right. All you will have to do is probably now change the executable name as we go forward, and also the number of processes you want to run the job on. Okay, now your first exercise, just to get familiar with Stampede, if you're not already familiar with it, is to compile an MPI program and run it using the script that you had. So you will use the command MPI CC -o MPI example4 to compile the program named MPI example4.c. And then you have to modify the job script, the one that you just copied, named run.slurm. Okay. In there, you will need to change the executable name after IB run. You will have to say IB run./MPI example4. I think I made a mistake in the explanation. I mean, yet another mistake in the in answering one of the questions. Frank asked whether, and maybe one more person asked whether the reading and writing process was blocking or non-blocking. I think I said non-blocking, but that's blocking. Now that I remember it more clearly, it will block, I think.
Yes.
Yeah.
When you call a variable, does that synchronize all the writing?
Yeah.
So what is the main difference then between MPI file write all and MPI file write? Is that write all the variables before, it like synchronizes things before it writes?
So the thing is, the write all is a bunch of optimizations built into it. So depending upon your implementation that you're using, it will automatically, maybe depending upon the, it will do some load balancing. You can think of it in that way. So depending upon the load, the amount of load that you're wanting to do, it will automatically do striping and invoking aggregators for a target number of things, and the operations that it chooses. Till, I mean, collective till MPI 2 standard were all blocking. But with MPI 3 standard, they're not non-blocking. So I'm not sure if they had like an update to the collective store IO as well or not. But now that the collective API are non-blocking, I think now it might be an improvement over the other version. But coming back to your question, so the main advantage of using that all thing is that you don't have to worry about doing so many things like stating like once you take data and you take the watches, the interest that can go on. So, but the only thing is, if you have a program in which like it is too small, you can engage multiple processes like it, which is one thing.
I mean, I'm just trying to get a sense for what context I should come to run all.
If you have like, if I were writing a program, if I have like data file to write, let's say a gigabyte or more, I would, in that case, I would definitely if I was small file, let's say it's less than a gig, I would just I did not do any of these experiments because most of the work I did for this is last year. So I do not know how the performance would be correct standard.
I would say one thing is probably the yours in between 1 and 10 somewhere in I switched all my life because I like to build 1 hour.
So you're on the So I had some.
Yes, I understand.
So
Let's say two strategies people have. Is this username?
Maybe you want to put your
Yes, my
tax username
I
in.
don't know what that.
I'm sure you log
You
in.
can, and that's what I'm
Oh,
going
yeah,
The system, right?
yeah, yes, that's awesome.
Yeah.
Yes.
I don't know if it's necessary or not.
Looks like it's just like it was before.
I assume that's email address.
Well, I'm going to talk about HTTP. Well, it's another way. Another way.
Okay, it probably doesn't matter.
So it's what's out there. David in this format that has metadata. So it's my go-to. I like having metadata. And I like it. I'll talk about this a lot. So HDF5 and that's there's some but I like HDF5 better overall. Because you want to have the ability to add more data without breaking the HDF5.
So if you are Fortran user and you do not like the C example that we have here, recommended for you to try, then you can grab another file from Train 00. It's called training MPI.tgz. Inside that, you will find some Fortran examples that you can compile using MPI F90 command.
Where is the Fortan again?
Go to train 00.
If it doesn't, then
Training MPI is the guide.
Oh, is that?
This guy has. So you see MPI example 8.
Which page is something?
Yeah. So the command for compiling MPI Fortran program is MPI F90 instead of MPI.
it's actually easier to just show Q minus U. I don't know.
Oh, let's go back to the job.
Maybe you might just be fire. So show Q minus U is show U.
So it's really what's.
In the way we would best use it.
That looks good. Submit this one. CS batch.
But that's show Q minus U.
It's run not stop.
Because there was this Lone Star script that we had in the training io.tgz, so we moved you to run.slurm. So that's what you must have copied from train 00 now. Now, when you're doing the batch job submission, after sbatch, you have to use run.slurm, not myjob.sh. That will submit the job. And sq is the command. If you give that, with which you can check the status of your job in the queue. And you can also use show queue minus u. That will also give you the same information. So this guy, show queue minus u. You can either use that too. It's all going well. Oh, let's see. If we scroll up, there is. It's not finding this might be a C. What was the name? Yes. Yes. So when what's
Looks like you're going to have some, here's some print. So it looks like zero. It's the sum total. This is the pattern. So each node has a range of integers. So one is going to sum from 1 to 100. Next one is 100 to 200. Some different ranges. There's partial. It looks like only it's 0 to some code. So it's called 5 years. You want all nodes to have this. So you got this stuff. Yeah, so there's two different applications. So this is you get some. Some and you will choose. You will answer only on node 0. Everybody needs to have an answer. Like just read zero has the answer. Everybody gets the answer.
Is everyone done with the exercise 0 so that we can move to the next exercise? Okay. So the objective of this exercise is that you just get practice of using MPI file write at. So there is a skeletal code called exercise1.c in the subdirectory or in the directory named training wherever you copied your files, inside it there would be exercise directory. So switch to that directory and you will find exercise 1.c, and there are comments in the code that tell you what to do. So first and foremost, you'll have to extend the variable declaration section, and then you have to have the MPI routine for opening a file. So you have a routine already in place there for opening another file for reading. Now you have to open a second file, okay? Its name is data file written. So you should have the right API to open this file and to close this file. And then there will be a comment which asks you to insert the API for MPI file write at, and you have to provide arguments for it. In order to see what all goes into MPI file write at, you might want to refer to the lecture slides. And after that, after you put in everything that is being asked for in these comments, then you compile the code and execute it using the script run.slurm that you just ran for exercise 0. So all you have to do is change the executable name there.
How do we get to the lecture slide?
Which one?
How do we get to the lecture slide?
Oh, they are posted online
They're available on the course page.
on the course page.
Which is,
What's the URL?
oh, just go to the TACC training page.
Yeah, the training page. And if you click on this parallel IO link, you'll see it there.
The Fortan example, that one is actually quite different. It doesn't involve reading. It doesn't use MPI file right out. It just, I mean, I know C2, so I think this is
Ooh.
it's just to finish these MPI file sent to, right?
If it's a different example.
And C doesn't like that, and the Fortan is like.
Well, I have that.
Awesome, sweet. Yeah.
I mean,
But thank you. Thank you. Okay. So this was missing.
well, I mean, I think that's probably it. So.
That's right.
Get a question suspect.
Right, right.
Yeah.
Oh,
So
okay.
it's different.
Awesome. Thank you. You don't. There are two things. Yes, you don't need to get this is not required. Closing the file. All MPI pass. I don't think we have recognition. Sure. Do we have a reservation number for the class? You would try to develop it. Build the development.
Just, we're not reading the finance, right?
No.
Just reading about what
Yeah. Because you're having questions. Okay.
I think we dropped down a little bit, but is that 91 over there?
Can use any for this. Data internal servability. Okay. Talking about. Finished? Ooh.
Are we all done with exercise 1 here? Okay, then I'll wait for a few more minutes.
And that's yes. So we can
Oh, sorry.
okay, do this. Except for program. So notice. That's
Oh, yeah.
yeah. That's right. So you go to the I will change this. See it again.
Okay, let's quickly move to the rest of the examples in there are related to distribution of 2D arrays, which I'm not sure if it's the right time to start that because Robert needs to cover HDF5 and T3PIO. Maybe I took longer than I should have taken. So what I'll do is I'll hang around. If Robert finishes earlier, we will come back to finishing the rest of the exercises. And for rest of the exercises, you'll have to get like one more example file, and it's called lab2 parallel.io.tar from train 00, and then we'll progress. We'll proceed after that. So I'll go find Robert, and I'll ask him if he can do this part. So there are 3 or 4 exercises that are remaining that we might come back to after Robert finishes his part.
So you create, it wouldn't write in.
Yeah.
Oh, so if you just choose create, you choose file, or can you just choose create, and then you check it. Because I will always open the file, but usually we writing the code. Then I never tried. Yeah, so I will going to use like that type, right? Then you put right here.
Okay. Oh, I got it.
So you can use a file. Yes. For the rest of the exercise, it's lab 2. Yes, that is right. I will grab a next later that will explain you. Do you all want to go on a break, like 5 minutes break for Robert stuff?
We're going to take 5 minutes to 10 minutes break here, and then Robert will start with HTF5 section. And only if time permits, towards the end, we will come back to lab session 1. Else we will proceed with lab session 2, wherein we have examples for HDF5 and T3PIO. Huh? Say again?
We will start back up at 3:20.
We will start back at 3:20. And that is Central Time.
Tired? Then that means you can close your
Yeah, I don't know. You do have to.
Yes, I guess. A scratch.
Oh, okay, well, I copied one on snow.
Oh,
One
that's
side,
fine.
make my own version. I always call my scripts job. So I'm always not, other places that I've worked, they call me anything you want. Some people did all the things we've done, our seismic processing jobs, we always, seismic processing scripts. We always end up full job. And, so that's my habit. It's easier to do what I need to have an understanding of it. Nuts. So I think I invited you to a party, and maybe I probably wouldn't be.
Let's see if it's a good
Yeah. My slides.
is.
You had a problem, you had a symptom of some kind. So I had to.
So am I good? I think so.
Yeah, you look good. And this mic is hot too.
Okay.
And I have the camera just focused over here, so you don't have to wear the lanyard if you don't want to.
Good.
It'll just hang out on the lectern.
Okay. Fine.
And advance with this guy.
Okay. All right. I guess we're going to get started on HDF5. I'm Robert McClay. I work here, and I'm a recent convert to HDF5, and so I'll be able to tell you my experiences with it. First of all, HDF5 is a file format. It's actually, there's a group that's been busy for 20 plus years called the hierarchical data format. There's an HDF group, and this is the 5th rendition of this, and they have several versions. We're up to 1.8 something or other, 1.8.12. Can be viewed as a file system within a file. It has sort of a Unix-like data structure. It's a mixture of entities, groups, data sets, and attributes. Any entity can have attributes, physical units, whatever you like. I think attributes can even have attributes if you like, but I'm not sure that makes a lot of sense. There are actually 2 versions of this. There is HDF5, and then there's the parallel version of this. And so we have, if you use the tax system, you can load HDF5, or you can load PHDF5 to get the parallel version. And you can write one file efficiently. That's what I'm going to talk about. And they claim that the parallel performance of HDF5 is very close to MPI I, and I think that's true as long as the file's pretty big and you're careful. But the nice thing is that Visit, ParaView, and TechPlot can be told how to read HDF5s directly. Well, you'll typically need a little text file that goes along with it to describe where your data sets are, but you don't have to rewrite them in another format and have HDF5 read them. So that's really convenient. So I've included a very abbreviated version of what an HDF5 file looks like. This is not exactly correct. I've removed things that weren't important to fit on the screen, but you can see the basic structure of an HDF5 file. So H5 dumps the contents of a HDF5 file. It tells you the name of the thing, and then it's got nested brackets. It tells you group is slash, so this is really the directory structure. And then data sets can be viewed as files maybe. And so I'm saying this is T for temperature, and I've got 10 values from 1.5 to 1625. And I've got an attribute with it, a description, and tells you this is my thermal solution. So you can put any text associated with a data set. Or you can attach attributes to groups as well. And I was just telling a few people, well, let me keep going. HDF5 has some advantages. If you only open one file for your solution file, you've got an efficient interaction with the metadata server. Every task calls HDF5 to write routines, but internally HDF5 and MPI move the data to a small number of writer nodes. Some of your processes duplicate as writer nodes, and we can control the number of writer stripes and stripe size to tune the performance, and that's this T3PO library. There are other ways to do it, but I'll talk about that. So here's the benefits of HDF5 for me are the benefits of metadata. While any format you have, you can put text in there that describes what you've got. You know, it's just if your file is a stream of bytes, you can just add more bytes to it. The problem is that if you've got standard binary I/O, then you add a new field. You want to know the version of your code, and you didn't have that before. Now all your readers have to know that you've modified, how the file format is read back. The advantage to HDF5 is you don't care how much, you can potentially ignore that stuff in an automatic way to you say, I just want to read this data set. And if you want to read an attribute, you can read attributes, but you don't care. So that's the huge advantage to HDF5 is adding new data sets, adding new metadata. Don't break your readers, because you can say, I want the thermal value, I want the temperature value, I want the velocity, I want the precipitation, or whatever. You can add those things and not break your reader. And that's really... Like an object file. Well, it's really more, yes, but it's really more like a directory. So if you've got a directory and there's a magic file in there, sam.dat, you don't care there's a bill.dat and a whatever in that, you're only looking for one file. So that's really a closer analogy than viewing it as an object. I mean, I guess you could view it as an object, but it's a really stupid one. It's more of a C kind of object rather than a C++ kind of object, if that helps. But with HDF5, you can add all kinds of things. So I love this. So one of the things I'm really passionate about is testing. I like to know what my programs do, and I want to be able to go back and look at my results. And one of the nice things about HDF5 is I can encode all kinds of information in it, and I can decide later I can add even another one that I didn't have before, and that's really huge for me. So I put in the name of the computer I ran it on, the OS version, I get the compiler name and version, the MPI name and version, my program version. That's really key. And my input files tend to be small, like 1,000 characters or less. So my solution file just has an extra 1,000 bytes in it, which is the input file. So I can reconstruct exactly what I did, or at least I know what I did, just by looking at the contents of the solution file. And if tomorrow I need to put in the color of my shirt in that file, it won't break any of my readers, because it's just another attribute. So this is really powerful. So PLL HDF5 uses uses the MPI I/ROMI, I'll explain what that means, to handle the parallel parts. And one can use the info object to set the number of writers and stripes. And we, namely me and a bunch of colleagues, have created this library called T3PO to help manage that. So the idea of parallel I/O is called MPI I/O, but there's a reference implementation that was part of the standard called Rome I/O, and pretty much everybody uses that implementation. So when I say Rome I/O, I'm talking about the MPI I/O implementation, but as far as I know, every implementation, at least on supercomputers, of MPI I/O is based on Rome I/O. MPICH is, OpenMPI is, the Intel one is, and VAPICH is. Is there anything else? Cray, I'm pretty sure uses it as well, although I'm no guarantees on that. But they modify it. So everybody's free to modify the reference implementation. So marketing is everything. TAC's terrific tool for parallel I/O, that's how I got the name. Or we started with the acronym first and then came up with a name to fit it. So what we know is that parallel I/O performance depends on the number of writers, the number of stripes, and the stripe size. And somebody previously asked about stripes. So to be clear, originally in the 80s, everybody just had a single disk drive connected to their computer. And this guy, his first name is Randy, had this idea. He said, well, why don't I put multiple disks together on a single computer and have pieces of one bit, instead of writing my file on one disk and a separate file to another disk, let me put a piece of my file on disk 1, a piece of my file on disk 2, a piece of my file on disk 3, and I'll at least get 3 times the writing performance because I can write in parallel. So this guy came up with this acronym, RAID, for Randy's Amazing Idea. They came up with another name which sounds more appropriate. Was it Reduced Array of Inexpensive Disks? Anyway, but I like Randy's incredible idea better, amazing idea better. But anyway, so that's striping in a nutshell. That's been around for a while. Well, the first slide that Ritu talked about was dividing up MD. We have OSSs and OSTs. Well, an OST is just a computer with a lot of disks connected to it, and then inside of that, it's striped in there, just like I described. But we don't see that. When we look at a file system, we say how many stripes it has. It really means how many OSTs our file lives on. And that's what we mean by striping. That, I have a file on 80 stripes. That means I have pieces of my file on 80 out of the 100 or 384 OSTs that are available on Scratch. That's what striping means. Hopefully, I've answered this guy's question. If not, he can send some ask some more. But anyway, that's the notion of striping, is that we have multiple computers that act as a stripe. That's what we mean. Now, how many physical disks it's on the OST, I have no idea. I don't care. That's that piece of hardware. I don't get to control that. All I can control is how many OSTs I want to talk to. So, and my colleagues and I did an exhaustive study on trying to get, now you've got, so different parallel systems have different rules. If you're on the IBM system, you just get maximum striping. Your file possibly exists on all the stripes that are possible. Luster, you get a choice. By default, on our systems, you get 1 or 2 stripes. And that gives you, for a single file, that's what you want. You don't want your 100-byte file to be spread across 60 OSTs, because that's just, you'll still live on one file and have the potential of being on all the other 60. But if you're writing gigabytes and gigabytes, you don't want them on 2 stripes. You want to spread them around. So that's part of the reason why we're teaching this class is this is more like a manual. It's not an automatic. You have to have some idea what gear you want to be in when you're driving. If you're going up a hill, you're going to be in low gear. If you're writing small files, you're going to be writing to a small number of stripes. If you're writing lots of big files, you have to control the number of stripes. So T3PO is a way to help automate that, but it's no magic. It's just got some heuristics in there. And one of the things we discovered was that stripes are everything. That if the file's big enough, you want to be on to get best performance, you want to be on a large number of stripes. Now, there are all kinds of rules on what you should choose, but you want to be more than 2. And if you're on 2, you're going to pay a huge penalty. And I'll show that. And there's a bunch of rules, of heuristics to decide, how many stripes you should have, but realistically, it's the number of stripes. And so typically what you want is the number of stripes, k times the number of nodes you have, be the number of stripes you have, up to a limit, where k could be 1 to 4. So you might have, if you have 10 nodes, you might want to write to 40 stripes. But 4 times the number of nodes is about the best you're going to do on most systems. Maybe you can do a little bit better, but there's a limit to how many stripes you want to be on. One of the problems you have is that Lustre is a shared system, so that when all of you are writing files, you're writing to the same hardware. Now, you may not be writing the same OSTs, although you're going to be in contention with everybody else. There's only 384 of them on Scratch. That means that if there are 100 jobs out there, there's likely to be contention for that resource. It's not like your job owns these 100 over here and nobody else can write to them. No, that's shared for everybody. When you're on a node, you've got the node. When you're on a node, only the operating system and you are on that node. There's nobody else using it. But the Lustre file system is a shared resource. And to get a scale, for people who aren't in this room, we're right next to Stampede. And Stampede has 8 rows of cabinets. There are 8 cabinets for the parallel file system. Okay? So that should give you a ratio of how much I/O there is versus how much compute power there is. It's just, you can get swamped. Okay. So here's some heuristics. The advantage is T3PO is it will figure out the logic for you, but you can do this on your own, and we talked about that. Well, it may have been the slides we didn't get a chance to talk about, but you can use this library. The advantage is it has a pretty simple interface. All you need to do is pass the communicator, an info object, and the directory, and the rest of it are optional arguments. For Fortran or C is pretty much the same thing. And what it does is it chooses the performance to choose the number of writers, the number of stripes, and the stripe size, and the parameter, the library will set it for you. Okay, so one of the things you've got to worry about is you've got to actually use this thing. Yeah?
There's a question about since parallel netcdf is built on PHDF, does T3PIO work with that as well?
Yes. So T3PO will actually work with any MPI I objects. So if you're writing straight MPI I/O or HDF5 or parallel HDF5 or parallel netcdf. Now, there are 2 versions of parallel netcdf, and I'm pretty sure it works with both of them for different reasons. But they all sit on top of MPI I/O, so they will use the info object. So the trick is that what T3PO is doing is it's giving hints in the info object, which then, when the file gets created by HDF5 or MPI I/O or parallel netcdf, it will set those. It will choose the number of stripes for you on a Lustre system. If you set it on another file system, these hints will be just ignored. So this is just to show you, and we lose the color here, but T3PO, you call it, you set the info object, it calls this HDF5P, which is, create a property thing, which is this plist thing, and then, oh, we lost all the underscores too, man. Anyway, so the things with the little spaces here are really underscores, and then you tell it this set FAPL MPIO tells you you're going to do things in parallel, and finally you open the file with this plist ID. And similarly, you do the same thing in C, where you create the file finally. And one of the things that people who have tried to use T3PO typically fail to do is they use T3PO to create the info object and then fail to use it when they open the file. therefore it doesn't do you any good. Oh, and the other thing is you can only create a file once. So if you're rewriting the same file, you better delete it before you try to rewrite it again. Because once you set the stripes and size on a file, you're done. You can't change it. You have to create a new file. Okay, let's talk about I/O. Okay, so we're going to talk about parallel I/O either with MPI I/O or the parallel HDF5. So my background's in fluid mechanics and parallel, and partial differential equations. So I'm thinking grids, and a lot of what people do is grids, but in some way you're going to partition your data, or that's a way to get parallelization. So I'm going to show two kinds of examples: one for a structured grid and one for an unstructured grid. And the unstructured grid might be just a vector. So a structured grid. This is just a simple 2D example where I've got, four domains, 2 in each direction. And I've counted them off 0, 1, 2, 3. And what I've drawn a box going across the very bottom to say, here's the data how I would like it written out. In other words, I want the data, if I want to write this data out as if one processor wrote it out rather than subdivided, that means the data is going to be collected from, if I write out the first row, I have to collect data from processor 0, processor 1, and keep working my way up. So I'm going to get bits and pieces. If I were doing this the dumb way, I would write out the first 5 elements from processor 0, write out the next 5 elements from processor 1, and work my way all the way up. That's the easy, the simplest way to code it, but the most inefficient way to get there. Whereas with an unstructured grid, you don't have that kind of behavior. Now I've gone to the trouble of dividing this into 3 domains, and I've happened to put the same number of nodes on each of the domains just to make the drawing simpler, but of course that's just a convenience of drawing. And I have to say I spent too much time making this drawing. I was trying to use OmniGraffle, and anyway, learning on the installment plan. But what I wanted to point out is that if you number your unstructured grid in such a way that the points are sequential, so that all the domain 0 nodes are numbered in such a way that they are connected, and then processor 1 and processor 2, that when you write the file out, you've got a very simple partition on the data. You just go, processor 0 writes out the first 5 elements, processor 1 writes out the second 5, and processor 2 writes out the third 5, and it's simple. Sorry. Well. So these are the 2 ways you might view your data, either from a grid point of view, or if it's just a vector and it's got nothing to do with a grid, you're still going to partition it up just like you did this one-dimensional partitioning, and you still want to write it out in parallel. So there are different ways to describe how your data is written out. So one of the things you have to worry about is you've got a big block of data. I've got a, what did I say? There's 10 by 8 block that I want to write out. That's what the global domain is. Whereas what I've got is I've got that broken up into pieces. So somehow, since HDF5 or MPI isn't going to know how your data is laid out, you have to tell it. So how do you do that? Well, there are various names as this goes by. HDF5 called them hyperslabs. There's this file view and other stuff that MPI talks about. And fortunately, it's about the simplest thing you could think of, although they put a $5 word for it. So hyperslabs are the way you describe your data. And it's pretty simple. It's what your grandmother would have told you if you'd asked her the right question, which is what you want the offset plus the size. So in a 2-dimensional example, I've got 2 numbers which tell me what the offset of my local domain is from the origin. So in this case, for processor 1, it's got a global offset in Fortran number starting with 1. I'm going 6 points to the left and 1 point up. That's my global offset.
and the size is 5 by 4. Okay? For processor 2, I have 1 to the left and 5 up, and again the size is 5 by 4, x then y. Okay? So how you describe your data is, and this is a very typical way to explain grid data, is you've got, pieces of it spread out, and I've done it in such a way that there's no overlap in the data, but you could just as easily blow them out if you wanted to do ghost cells, 1 or more in each direction. Although you may not want to, well, depending on how you do things, you may write them out in one format and read them in one format and write them out in another, because you don't want to duplicate the data. So you might write them out so you have unique data on each processor, but when you read it back in, you might want to have the ghost cells. Either way. Okay, so I put up this straw man. The straw man is with and without T3PO. And in some sense, I've put the competition in as about a worse a light as possible, in that this is with T3PO and without T3PO. And what that means is that this is the performance, and the performance goes up to, something along the order of 6,000 megabytes a second, versus doing about 500 without T3PO. And the reason why I'm doing so much better with T3PO is the blue line is just 2 stripes. So no matter how big the file is, I'm not getting any parallel performance. No matter how many nodes I've got or whatever, I'm not getting any performance. Whereas T3PO, it will choose the reasonable number of stripes, so you get much better performance out of it. Yes?
Do you know how many nodes are used to do this?
Probably 40. Not a big number, but
So more than 1.
oh yeah. Well, the 1 would have been down here at the blue line. No, but this is like 40 nodes. But 40 nodes, if they only have 2 stripes, there's just no benefit. I don't care how many writers you've got. You've only got 2 stripes, and there's got 2 lonely OSTs, just one-armed paper hangers. There's just only so much they can do. So that's the beauty of striping, is that you get parallel performance. How about that? Now, this is not the only way. This is not the only way to get parallel performance. You could create a directory and define that directory to have the default for that directory is 40 stripes or 80 stripes or whatever. But you have to remember to do that each time. Now, maybe if it's part of a job flow, that's okay, but T3PO will do that automatically. So that's another way to do it. Or you don't have to call T3PO. You can set those. You can call the info. What all T3PO is doing is looking at the size of your file, how many nodes you've got, and then giving the MPI I hints. So you can do that without T3PO. But one of the things I wanted to point out is it is a shared resource. So these 2 figures are essentially, well, the red line in both cases is the same. It's just that the green line and the blue line represent the green line is the worst performance of, this was with 10 runs, and the green line is the worst 1 run or worst value for that file size, and the blue line is the best performance. So on a good day, you're getting above 7,000 megabytes a second, but that was only 1 run, whereas on average, you're doing a little worse than 6. But you've got contention. There's nothing you can do about it unless you have a spare 50+ million to have your own machine just for you. But that only buys you about, just a little bit better performance, so probably not worth it. Structured grid, unstructured grid. Why am I duplicates? Okay, I can skip that. So let's talk about HDF5. HDF5 can be viewed as an onion. So you've got outer layers, or if anybody's seen lists, these are just lots of parentheses. We're going to start from the outermost one and work our way in. So you're going to open, you actually tell the library I'm going to start using HDF5, and then at the very end you're going to close it. Then you open a file. If you want, you can open a group. You can open a data set. You can write a data set. You can close a data set. You close a group, close a file, close HDF5. So you just got to keep opening up the onion and get into far you want to go, and then close it back up. Yes?
In your graph, what was the maximum stripe we got the best performance?
If it was 40 nodes, it would have been 80 stripes. So again, I've shown this HDF5 dump of the file. You can see that the structure is basically there. I've opened the file. I've got groups. I've got a data set, and I've got an attribute, similar to what I showed. Okay. Now, this is just, there are lots of ways to handle parallel data. This is just my way of handling this. I like to have a little struct which describes sizes. So I just pass it, instead of having, integer values that I pass in my routines, I like to conglomerate into this little struct, and I find this grid type in Fortran or doing the same thing in C to be quite useful. So this thing allows me to do 2 or 3 dimensions, so ND is the number of dimensions, IS is the start, IE is the end, and N is the number of points, and max dimension in this case is 3. So I just pass around object of this size. So I've got a structured grid. I can just pass this little piece around, and I just find it a convenience. And I point that out because I'm showing you how I'm taking this local. So I have a local and a global version of these things in order to tell HDF5 what these things are. And unfortunately, HDF5 doesn't know about my favorite struct, so you have to translate it into get the starts, the size, the global size, and these last 2 numbers are just to give me how big the local size is and the global size. The point is that, but I point this out because even though it's got a Fortran, HDF5 has a Fortran index, in Fortran interface, it still wants 0-based numbers. So internally, it's not doing this for you. You have to tell it. So starts, I've got, this is a Fortran code, so my indices start at 1, but it expects the starts to be at 0. Okay, so here's the real code that shows, or shows the example. And so, step 1, I open the file. Step 2, I'm going to create this parallel open, or I'm going to create this parallel property, which is setting this plist ID, and then, again, the underscores have been ripped out. And then I open the file, and then I create the group. This is, you create this H5P creates a property list. You open the file, and then you close the property list, and then you create a group. I wanted to create a group, and I added a description to it, and then this loop here, I'm going to explain this over the number of variables, and then I'm going to close the file. Sorry, I'm going to close the group, close the file, and close HDF5. So that's the big onion, and I'm going to show you the interior of the do loop on the next 2 slides. So here's how you describe the hyperslab to HDF5. You're going to create this file space, and then you're going to create this mem space. So this is the global size, the local size, and you can see, the number of dimensions is going to be 3. The global size is there, and it's going to create this file space thing. That's the global hyperslab, and then here's the local piece of it, which is based on sizes, and then finally there's the start here, which tells this creates these data sets, and then we're at the bottom. We're going to create the hyperslab, and this step in the middle. Oh yeah, you can give it properties. Oh, I'm going to create the data set. Oh yeah, okay. So here's one of the things that also, okay, I really like HDF5. I think that their tutorial page is excellent, and that's about it. The rest of the documentation there's a lot of it, and I found it completely impenetrable. I almost want to just bang their heads together and say, what are you thinking? But one of the things that they talk about is data formats. And they talk about, well, you ought to choose a data format that makes sense for you. Well, they probably wrote this back in the 90s where there was a choice. Should you be little endian or big endian? Little endian or big endian? Well, maybe most of you don't even know what those words mean, but in case anybody cares, the big endian camp is pretty much dead, and there's only little endian left. So you should just write. You should just write in the native format. You can tell HDF5, I want the native format, and it knows that it's little endian, or at least our system is little endian, And if it ever has to translate it to a big endian machine, it will just do that. But since most of the world is little endian, you might as well just stay with it. That's one of the documentation things. I couldn't figure out what the hell they were talking about. Okay, so you create a hyperslab. Then once you've created the hyperslab, you're going to create the data set, create create a property list for the data set, right? Tell it you're doing MPI I. This is what this H5P thing, which sets the transfer mode. I like to write attributes out, but the step 8 is the key. It's where the data set is actually written, and then you close the file space, the mem space, and then close the file and close the plist. So it's just, so here's the inner part of the loop. Now we've actually written the file. So it's a lot of steps, and some of them make sense. Some of them you just have to drink the Kool-Aid and say, okay, this is the way you use HDF5. I think these guys are database guys, and they just don't understand how we think. But, it's the way it is. So, so one of the things that I want to point out to you is, as I said, understanding HDF5 I think is worth the time and effort, but it's tough. And so when we have an example where we're going to show you as part of the lab, but if you really want to understand it, you probably need to go to the HDF5 tutorial page and start with their examples. That'll get you pretty basic stuff, but not even teach you how to do the parallel I/O stuff. But as part of, T3PO is out on GitHub, and you can download it. And one of the nice things about it is it has 2 complete work examples. There's a thing I call cube test and an unstruct test. And the cube test is a Fortran structured 3D code that essentially these examples, the slides I produced are from. And there's also an unstruct version of a C++ code that's completely worked. So you can see see all the pieces which are not explained in the tutorial. So there are, so that if you want to understand HDF5, I think that once you've gone through the tutorials, studying the T3PO example codes, I think is at least a good way to do this, because otherwise, it took me months to understand what the hell they were really trying to do. Whereas I think hopefully I will save you some time. But there are some other resources out there. Oak Ridge has this wonderful talk, and there's some parallel talks by this guy Thacker, who was a part of the Rome I/O implementation team. So we're ready for the lab. Okay. Any questions before we go to the lab? Okay. Well, go to your Scratch directory, unload the tar file, and hopefully you can see hopefully that will all be laid out correctly this time. So is it laid out correctly, or do you have to copy it to a directory and then untar it there? Huh? Oh, is it just there? Where are you?
The tar.
You do not need the dash. You can say XVF. It works with or without. Okay, let's see what the next. Oops, same slide. Oh, there's an MPIO one and there's the HDF5 one. They're two subdirectories, and you can choose which one you'd like to work on. There's the HDF5. Anyway, there are subdirectories there, and you can tells you how to build these things.
A can be, yeah. Right, so start with DL5, that
Oh, you have to load the module.
Oh.
You have to load the PHDF5.
If I say that.
It may not have.
That.
Sure. Well, you just do it with the you set S batch minus A and then TG whatever in the job script. Oh, there's a minus A option to it, I believe. Yeah, so it should be module. Yeah, so okay. There's one other thing I should have I remembered now is that those examples at R&T 3PO, the cube test and the unstruct test, have both HDF5 and MPIO in them, so you can sort of use them as a Rosetta Stone to see how each one is done.
This is the output. Yeah. So right here's, notice that when it's down in here, it's splitting it. Is that because it's so smart that it knows how big my screen is?
Yes. Well, or maybe it's
It has some
yeah.
So here's root. This is getting smart, not splitting.
Right.
Bigger, more digits, so output.
Yeah, so as I said, I would yes. Now there's also the H5LS. There's a H5LS. Tells you
What you got?
yeah. So if you have properties in there, you get this information without this. So it's sort of like the Cabinet file versus LS.
Sure. Right.
No, not yet. The only, if you like the fact, like the file, isn't on, you only choose strategy. Written. This one. Use that. So you have to write it parallel. But you have to, you can write it, you can have one processor. So that's not a problem. But you know, when you want to choose it, right? For many people in simulations, you like more than I might like 100 times the last. Right? Whatever. Well, but, you know, but in general. Yeah, so I'm very concerned about writing efficiency. I write more than that. If you write once, read back, then you won't think about is adequate. Writing parallel, reading back the process, maybe doesn't writing at once. But you have to make design decisions. I think it's important. But setting the number of stripes, writing makes a lot of sense to be worried about that. But we have to do that. But that is the graphics. But it depends on what you're working on. Basically, either the writing efficient, writing part of the change process, but maybe not like start using it. But if you read the writing of the process, making that choice for the writing also. But it's even strong. Yeah, but the stripes, right? So, yeah, I have converted to it. Not the data is parallel as well. Oh, I see. No, you got no. Right. Research. You got no. I've got no harm basically. But I want to see. And then it gives you the offset. Then they got to read it. That's it. You did not have money to get. I'll tell you what. So, when you do that, you would have to open the file and then there's some how do you know what you say? Oh, you have a file. You know, yeah, I understand. No, I'm in the things that I'm really detailed. Luster process. That's stuff. And then first, once you break that down, once you get to whatever the time you call. Yeah, so like actually, what we could do as one of this is that it's on stack. Now, this is more style, that's the stack. The idea is pretty tough. The way that they have I know what I'm saying. Create one. It has a program directory. Update the file, change the permissions, open the file. Separate that. So if you have lots of files, a series of some work on your data, on your project, you set up an HTML that contains all of your data in the project. It all has inside kind of like a Linux file system. But it's all bundled up in one big file. And so anytime you want to look at your data, it's in your file. It's not in that single node that everybody understands. You only have to open one file. For these large clusters, it avoids the problem. I don't know what MPI is. MPI is
Yeah, and there's no, as far as I can tell, there's no.
yeah. You have to know those numbers.
That's,
But you can do it. It's not-
yeah.
That's why I default. That's why I like. No, that's wrong. Oh, no, the summary is when I wrote it from scratch. I wrote that one from scratch. Yes, I wrote that one from scratch. No, it's always on. That's useful on one. And I got stuff. You're at the sometimes it's strip it out of the file, process it, and merge all back together afterwards. It's an built system of thousands of files that are
instead of having one file that's 200 megabytes. It's gonna kill the system.
Hello.
You do that on Stampede.
No, I'm not.
You do that on Stampede. Yeah. File. Labels. Time. X. Y. I see this in the break the data. I'm going to have this. This forward. Create 1,000 files like that each of these files.
Yes.
And then you, after the loop, you have a flow with some sort of an SF cap. And the flow that merges them all back together. You do stuff like this, and then you try to, oh, I'm just going to yes consoles. And put it out. Those, kill 1,000 files out of you. It's going to go out there. It's going to make a real problem. So you don't want to poor way. We're talking about poor way of using the system. Yeah, it's a serious problem. I don't know what the solution is for that gas pipe. The way that we used to run it. And this doesn't work very well. We would have a task, take a piece of this file and process it and put it into the system. So we run a job, create this file, run a task, flow to create this, and we run one task for each piece of data. Accumulate the results of this data. And we wouldn't actually make separate files. But Madagascar's not going to do that. It doesn't know. So this, you got to know.
Yeah.
So here's I don't know. I think what this demands is I think it might maybe it goes to the permissions on the file. Tries to find out.
He's got a display on that.
So you have, so where these tools are used, so yes, traditional structure. Partition-based nodes are connections like this. So you're using those and hold them pretty centralized connections. Partitions on the nodes. So actually what you've got, here's this way. I'm supposing if you want to use a tool like this, these are space that so the map, so the map here. Yeah. So I think what the other tools is actual grid. X and Y. Just and then that's what cases are up to you have the combination grid. And then you have another case combination. So in this case, so you have one of these processors. You have a processor right there, and he's supposed to get this piece of data. So the data might be laid out on disk. The data might be laid out in 3 pieces. You might have to strike it 3 ways. You want to strike it 12 ways, whatever the data is. So you need to read the data and strike broken into 3 pieces. 3 separate files. You need to read it in memory. That's right. So problem. So you have reverse time migration. You're doing your reverse time migration. One hundred Y, so 100 X, 100. Say you decide and your project is some size, so it's going to have certain chunks in each of these directions. So, but the data when it first came in, you have
you mean at one point, that's all of them. That's not the wise. Just the access
You have one shot like in the process, trying to do your wave propagation. When you experiment, you have everything all laid down, data is laid out.
Actually, just access, grade, one. Yeah.
The more we, if you have the inside, you might have 100 nodes that are processing one shell.
Yeah.
And the order that your data, so when you're doing the reverse time migration, I guess the data is laid so on the surface, you read that different things. And I think that this, your HDI, the other two, the T3 IO, that's designed to help you. You know, if you have your data all laid out, I guess on our problem, you want to read it to help you distribute those data. Maybe it's more applicable with maybe the problem is more applicable with understanding. Typically what you do is you forward propagate the source and say,
Yes, that's true.
and I think that this T3PO is going to help you do some of those reorganizations.
At this stage, generates that successful.
In that case, I think what happens is you have all the data. It's just the number of stripes that you have to use. So you're pushing the data out on those nodes. Maybe you want to run on 100 nodes, but you want to have a different.
It makes sense.
So you also, it's always,
So yeah, that's all that you, and then you say, you set all this stuff up and you say, okay, now I want to read the data and each of the nodes from this.
yeah.
So into the node that needs it.
Yes, yes.
Reorganize it. So. Been a long time since I wrote this thing. It's somebody else's problem. Things are changing a lot. Difficult stuff.
Yes.
And you start having boards and program variables and each of those boards and because you start with the end because you start with this block. Which so when you search through all these places, you always try to start with this. I've nested. Look, four places. Each subdivision is four. Start with a triangle, break it into four. You've got a square, so it's four places. And then look at the stuff. Bells, like a bells, actually. Four, but it's only four happens. So you're using yeah. Bang, bang, yeah. So other places do this. I had a I call this competences. Which you say on keys. Go on here and so that's how I do what you do is you can walk the boundary and go on to go through each place and then go to the walk. But I think with a nesting like this here, really good time search. Now whether that helps you or not, I don't know, but that's what natural things. I can remember something that is 25 or something. That's all it's going to There are all kinds of avenues. Area coordinates. Size of triangles. What happens is you get two of them, two possible user, and there are all those who are very that's the natural way to do it. Everything that's supposed to be, even outside, right, in this case, this perception of we work with so he's distracted in here. I would use
There's an else to that.
but hiring still doesn't. Yes. But usually that so that's what I hired. That's what I hired.